Hello everybody, today we're going to talk to you about two-dimensional kinematics. First off, it's important that you understand parabolic trajectories. Parabolic trajectory occurs when an object is launched and is under the influence of no force other than that of gravity. This includes air resistance and other frictional forces. Upon its launch, the object will follow the path of a parabola. Real-world examples of objects that follow parabolic trajectories include a basketball thrown towards a basket or a cannonball shot from a cannon. There are two types of projectile motion that we'll look at in this video. The first of which is a projectile launched horizontally. Horizontally launched projectiles are objects that are launched with an initial horizontal velocity but no initial vertical velocity. We can solve problems with horizontal projectile motion with the kinematic equations split into horizontal and vertical components. In all of these problems, certain things hold true regardless of situation. Horizontal acceleration is 0, horizontal velocity remains constant, vertical acceleration is g, initial vertical velocity is 0, and time holds the same in both directions. The remainder of values are provided as given in these problems. Now let's look at an example of a horizontal projectile motion problem with a demo of a ball rolling off of a table.
So in the example video you just saw, the ball traveled a vertical distance of 3 meters with a horizontal velocity of 2 meters per second. In black, we have the values that hold true regardless of the horizontal projectile motion problem that we explained in the previous slide. Now we can use these values in the vertical direction to solve for time in order to find the horizontal displacement of the ball. Negative 3 meters equals initial velocity in the vertical direction is 0, 1/2. Acceleration in the vertical direction is negative 9.8 meters per second, t squared. When you plug in these values, you'll find that t equals 0.783 seconds. Now we can plug in this time value in the vertical direction for the horizontal direction as well, as time is the same in vertical and horizontal directions. When we plug that into this equation down here, we'll find change of x equals initial velocity times time, and acceleration in the horizontal direction is 0, so this will cancel out, and we'll come out with our final answer that x equals 1.56 meters.
The second type of projectile motion is a projectile launched at an angle. These objects are given both an initial vertical velocity and an initial horizontal velocity. We will solve these problems with the same way as horizontally launched projectile problems, with the kinematic equations split into vertical and horizontal components. Certain things hold true in all of these problems as well. Horizontal acceleration is 0, horizontal velocity remains constant, vertical acceleration is g, and time is the same in both directions. The remainder of values are provided as givens in these problems. Now let's look at an example of a projectile launched at an angle problem with a demo of Elise hitting a golf ball.
In the video of Elise hitting the golf ball that you just watched, the initial velocity in the horizontal direction was 4 meters per second, the final velocity in the vertical direction was negative 2 meters per second, and time was half a second. The acceleration values that you see in black hold true for all projectile launch at an angle problems. Now in the vertical direction, we can find initial vertical velocity. Here we have 3 out of the 5 values for kinematic equations, so we don't need to worry about the horizontal values. We can plug in these vertical values in order to find the initial vertical velocity. Here, final vertical velocity was negative 2 meters per second. Vyi is what we're finding. Acceleration in the vertical velocity in the vertical direction is negative 9.8 meters per second, and time is 1/2 of a second. Plugging in these values, we'll find that the initial velocity in the vertical direction is 2.9 meters per second. That's our final answer.
Now let's talk about air resistance. In both of our demos, we ignored a force called air resistance. Air resistance is a frictional force between air and an object moving through it. Air resistance opposes the object's motion and impacts objects with high speeds and large surface areas the most. In problems like our demos, we often ignore air resistance because it is essentially negligible in most of the problems we do in this class. The ball in the first demo and the golf ball in the second demo have relatively small surface areas and aren't moving too quickly, so the force of our air resistance didn't have a large impact in either scenario. Another topic we're going to look at is relative motion. Where an object moves, its motion can appear different depending on the perspective of the viewer. In typical situations, we refer to an object's speed relative to the Earth. However, an object's speed can be measured relative to anything. This is called relative motion. In the image, a runner is shown running at a constant 5 meters per second. However, to each of the 3 spectators, he runs at a different speed. The speeds of the spectators influence the runner's relative sped to each of them. Because Amy is standing still, the runner appears to be moving at 5 meters per second. But because Bill is biking at the same velocity, the runner appears to be at a stationary 0 meters per second. Carlos moves at 15 meters per second, 10 meters per second faster than the runner. So to Carlos, the runner runs at minus 10 meters per second. In actuality, the runner runs at the same speed, but his relative speed changes by perspective. This holds true for all objects. Relative motion is often applied in problems with animals flying against wind or boats moving against the current.